Intermolecular forces of attraction, A-level chemistry. Intermolecular forces of attraction are forces of attraction between covalent molecules. These are much weaker than ionic covalent and metallic bonding. We can only see it between covalent compounds. Normally, these forces of attraction will affect the boiling point and the melting point of the molecule. This is because energy will be needed to overcome these forces of attraction in order to melt or evaporate your compound. There are three different types of intermolecular forces. The first one is the permanent dipole-dipole intermolecular forces. The second one is the induced dipole-dipole, or which we call van der Waals forces of attraction. And the third one is the hydrogen bonding. In this video, we only talking about the permanent dipole-dipole and the induced dipole-dipole, and there will be a separate video for hydrogen bonding. So the first one is the permanent dipole-dipole forces. Polar molecules which have permanent dipole have weak electrostatic forces of attraction between the partial positive charge and the partial negative charge on neighboring molecule. So let's see an example. An example of that is hydrogen chloride. This is a polar molecule with a permanent dipole. It has a permanent dipole and permanent polar bond, and there is a neighboring hydrogen chloride molecule where there is a partial negative charge on all of the chlorine atoms and there is a partial positive charge on all of the hydrogen. They will arrange themselves where the partial negative charge of one chlorine is closer to the partial positive charge of a neighboring hydrogen of a neighboring molecule. There is an electrostatic interaction, weak electrostatic interaction between the partial negative charge on one chlorine of one molecule and the partial positive charge on the hydrogen on a neighboring molecule. This is called permanent dipole-dipole forces. We can also see that in something like chloromethane molecules, where there is partial positive charge on the carbon and partial negative charge on the chlorine. There will be an electrostatic interaction, weak electrostatic interaction between the carbon with the partial positive charge and the chlorine on a neighboring molecule with the partial negative charge. These intermolecular forces of attraction will affect the boiling point and the melting point of such molecules because we will need higher energy to break these intermolecular forces of attraction. However, these are much weaker compared to ionic bonding, covalent bonding, and metallic bonding. Remember, when you melt or evaporate molecules, organic molecules, you don't break the covalent bond, you only break the intermolecular forces of attraction between the molecules. The second type is the induced dipole forces of attraction, which is also called the van der Waals forces of attraction. You can find these between all atoms and molecules. Normally, when you have non-polar molecules, there will be the center of the negative and the positive charge will be identical. However, the bond in non-polar molecules, or when the bond is nonpolar, the electron cloud actually is continuously moving. So at any minute, a temporary dipole can be created, as we can see here on the right-hand side bond, where a dipole is created in the right molecule by the movement of the electron. This will induce a second dipole in the neighboring molecule or in the neighboring bond. This is going to be an induced and a temporary dipole as well. And then there will be electrostatic interaction between the electrostatic interaction between the induced dipoles, where it's very weak forces, and these are called van der Waals forces of attraction. Van der Waals intermolecular forces will hold molecules in a lattice, as we can see in iodine molecules. molecules, for example. Stronger van der Waals forces of attraction will lead to higher boiling points. So where can we see stronger van der Waals forces of attraction? We can see that under the effect of the size of the molecule or also the shape of the molecules. So in terms of the size of the molecule, the larger the molecule, the larger the electron density, which means there will be stronger intermolecular forces of attraction between the molecules. So there will be higher boiling point. For example, the longer the hydrocarbon chain, as we have learned before about the hydrocarbons, the higher the boiling points because the size will increase and the electron density will be higher for the whole molecule. So there will be stronger intermolecular forces of attraction. What about the shape of the molecule? Branched shape will have lower boiling point compared to straight chains. This is because straight chains are arranged more closely to each other, which means the van der Waals forces of attraction between the molecules will be stronger. So more energy will be needed to overcome the stronger intermolecular forces of attraction, and that leads to higher boiling point. We can see that if we compare branched chains of hydrocarbons compared to straight chains. So branched chains with the same number of carbons will have lower boiling points compared to the straight chain with the same number of carbon